So, Barth-Savart law is one way to calculate magnetic field if the current distribution is given. But for symmetric current distributions, there is another extremely good method which we call Ampere's law, and that happens to be much more fundamental equation for electromagnetism. So, we will be starting this chapter on Ampere's law today. From Barth-Savart law, we understand that the magnetic field B, because of a current, line current is mu naught by 4 pi, then current dl, this is the element, current element, and then cross r over r cube, and then we integrate under proper limits to get the magnetic field of a given current distribution. This can also be written, because this r vector, you know, if you have a current circuit and then here is that dl, here is that dl, idl, and then this is the point where we want the magnetic field. So, this vector is r vector, and it is this vector which keeps changing as you take that dl here, 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 here. We have another way of expressing. We take some origin somewhere, and then first, since we have to vary this, we write the position vector of this number, and this is generally called symbol r prime, O here and A here. So, r prime we write for vector from the origin, which is fixed, from the origin to the current element. So, here is the origin and here is the current element. So, from the origin to the current element, that we write as r prime, and then this dl also we write as dl prime. This dl prime is our length element. So, anything related to the current distribution, we are using this prime here, r prime, dl prime, and so on. And then the point where I need the magnetic field, that is denoted by vector r. This is denoted by vector r. This r is not this r. Okay. So, this r vector, that we write for position or vector from the origin to the field point, to the point where field is needed, we call it field point. And the vector from the current element to the field point, okay, vector from the current element to the field point. This is what we had written here as r vector, from the current element to the field point AP. This vector is coming here, this vector is coming here, the magnitude is coming here. So, vector from the current element to the field point will be now r vector and minus r prime vector. This vector, this will be r vector and minus r prime vector. R vector is from O to P, and this r prime vector is here. So, minus of r prime will be A to O. So, A to O is minus r prime, this minus r prime, and then plus r is this. So, if you come from here to here and then here to here, you add these two vectors, you get that AP. So, this is that vector from the current element to the field point, and then this dB, now the symbols will be different, it will be mu naught by 4 pi I dl. So, I, and we will write as dl prime, and cross, this is the vector from the current element to the field point, and this is now r vector minus r prime vector, and magnitude of this cube. So, the magnitude of this is r minus r prime mod and then cube. So, this is how the Bat-Savart equation is rewritten, and why we have written it this fashion will be just clear once we go for the Ampere's law, statement of Ampere's law. But before that, this is linear current, there is a wire, and then only length is important, and we say that okay, it is a linear current, and here is the current element. If it is a surface current, this is for linear current. If it is a surface current, then we write this as mu naught over 4 pi, and I dl prime will be now k vector and dA prime. This is the current element. If it is surface, we had done an examples on the surface current, magnetic field due to surface current, and if this is the surface current density at this location, this is a surface here, this is a surface, and then there is current on this. Then if I take certain point here, at that point I ask what is the current density, what is the direction of current, and how much current is going per unit length, dl length divided by dl, that k is here, and where at a certain point, and you construct an area, and everywhere in the small area which I call dA prime, and that area will be now at r prime vector. Just like this length element is at r prime vector in the current distribution, linear current distribution. Here the current is on the surface. So, on the surface we take a small area, and then k times dA prime is the current element, and the location of that current element is this r prime. That is it, cross r vector minus r prime vector. You need this magnetic field here, and this vector is r vector, and this vector is r vector minus r prime vector. The remaining geometry is same, this divided by mod of r minus r prime cube. If this is surface current, if it is volume current, you have a volume, and everywhere in the volume there are currents, then your expression will be correspondingly modified, and that will be mu naught by 4 pi, and then J volume current density, and this is now d tau, small volume element, and in that small volume element d tau prime, where at the location r prime vector. So, you take your small volume at r prime position, and then see what is the current density, volume current density there, which we write j d tau, that will be here, and then the remaining thing will be the same. This is if you have volume current. Now, the volume current is the most general kind of current, a linear current, a surface current. that everything can be expressed as a volume current. Even if I have a line and then there is a line current, it is good that there is a line current. First the line will have some thickness, it is, of course it is a wire, it is not y equal to mx plus c, the straight line that we study in geometry. It is a wire, it is carrying current, so there has to be some thickness and therefore some volume. Similarly, if you have a surface, then the surface will have some thickness and it will become volume. So, this is one. Even if I mathematically, even if you take a mathematical line, that line can also be written using those Dirac delta functions as a volume. This surface can also be written as a volume, this line also can be written as a volume. Even if you neglect the thickness absolutely of the surface of the line, even then I can write that in terms of Dirac delta functions that we had done perhaps in the previous course, but nevertheless mathematically it can be done. So, every distribution can be written as a volume distribution. So, we will be writing our equations using this, and then whatever is the result, that will be applicable for everything. Now, suppose the current distribution is given, fixed, it is a distribution. At any point if I need the magnetic field, I have to integrate over all these small elements to get the contribution from the entire current distributions, that is fine. But then once the current distribution is known to me, extended, I can ask the magnetic field at this point, at that 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 point. So, the magnetic field is a function of the position of the field point, that is now important. This is the field point, and to get the magnetic field here I need the whole integration, and therefore all this r prime and dl prime and d tau prime, everything. But I can get the field here, that will be at position r. This point has position vector r, origin is here, x, y, z axes are there. So, this is position r, and this r can be varied. I can ask what is the field here, 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 what is the field here. So, B is a function of this position r of the field point, magnetic field due to a given current distribution. So, it is a vector field, we call it vector field, means at every point in the space you have a value of that vector, direction, magnitude. So, that kind of this vector is called vector field. So, B at r is a vector field, we call it vector field. It is a vector quantity, it is a vector quantity, and then it depends on location in the space. At different locations the value of this is different. So, that is known as vector field. You also have a scalar field where it will be a scalar quantity which will depend on position in space points. For example, if temperature in this room or in this town, so at different places, at different locations the temperature is different. Temperature itself is a scalar quantity, and temperature here, temperature there. So, at different space points you have different temperatures. So, temperature is a scalar field, and this quantity is a vector field. Now, for any vector field, two operations are very important, and those operations are divergence and curl. So, there is an operation called divergence of B. What is this? What is the divergence of B? The symbol is this inverted triangle and then a big dot and then B. So, this is the symbol. If somewhere it is written like this, you will read it as divergence of B. And what is this divergence of B? So, B is a field, everywhere there is a value of B. You suppose there is a space point there is a space point and I need what is the divergence of B here. I know what is the magnetic field here, I know what is the magnetic field here, I know what is the magnetic field here, I know what is the magnetic field here. That B is known to me at every point. But then there is some quantity called divergence of B. So, what is the value of divergence of B at this point? So, make a closed surface or take a volume, small volume enclosing this point P. Take a small volume around this P. P is inside that volume. So, we construct a small volume. This is a small volume and the volume, let me write, is delta tau, and then this point is inside the volume, right. So, here at this location you construct this small volume, then there will be surface, closed volume means there is a surface and this P point is inside. On this volume you again take some dA surface, dA, and make this area vector. What is this area vector? You draw a perpendicular in the normal in the outward direction. Since it is a closed surface, we know what is inside and what is outside. So, on the surface of this closed surface, you take a small area and on that area you draw a normal which is in outward direction, okay, and do it for all the sides here, everywhere, and construct this quantity B dot dA. Construct this quantity. It is a closed surface, and since we are taking this dA everywhere on this. So, suppose the volume that we take here is of this kind, right. So, inside there is a point P and around that point P we have constructed this volume, and here is the surface, this is a surface, this is a surface, this is a surface. This whole thing is surface of that closed volume. So, what we are saying is that on this surface you take a small part, that whole surface is also small, remember this whole volume is very small, we are going to take the limit when the volume goes to 0, but even then if it is a volume you will have surface this side, surface that side, surface this side, surface that side. So, on this surface you take a small part and then draw a normal perpendicular to this surface and in the outward direction, so this way. So, this is that dA vector I am talking, and at this position there is a value of B magnetic field or any field, any vector field. So, B is just a name for the vector field at this moment. So, you have some magnitude and some direction of this vector B, and then dA vector there is some magnitude and some direction. So, take that B dot dA. Here what is the direction of B, what is the magnitude of B, that is right here, and then this dA, this is normal and the magnitude is dA. So, that vector is here, and do it for every small part on the surface of this volume. Here, if you take the area here, then this is the dA vector. If you take an area here, this is the dA vector. If you take an area here, this is the dA vector. If you take an area here, this is the dA vector, and here you have a value of B, here you have a value of B, here you have a value of B, here you have a value of B. So, everywhere on this surface you have a value of B. Construct small areas on this surface, add all those contributions and create this quantity and divide it by the volume of this whole thing, delta tau. Okay. So, once again I repeat, to get the divergence of a vector field at a given point, space point P, you construct a volume which encloses this point P and then the surface of that volume, look at that, and on each small part of this surface you see what is the value of that vector field B, magnitude and direction, and there you construct that small area, the vector area, the perpendicular outward normal, that is the direction, and area, actual area in whatever unit, millimeter square, micrometer square. So, and then do this dot product B dot dA, add on the entire surface. So, that is this numerator, and divide it by the whole volume which you had constructed. So, that volume, and now take the limit of this, now take the limit of this as this delta tau tends to 0. So, that means this operation is to be done on a very small volume, very small volume, very small volume. So, you take the limit as this delta tau tends to 0, that quantity, this quantity is known as divergence of B at P, at this point. If you name this point as P, then this is divergence of B at P, is this. To get the divergence at another point, do this entire operation there. Take a small volume enclosing that point, once again look at the surface, once again see the outward normals, once again do that B dot dA everywhere, add them and divide by that volume, and take that volume to be 0, going to 0. So, at every point in space you can define what is divergence of B. This is for a general vector field, any vector field. Now, operationally every time you do not have to do this. You do not have to do this every time once you want to know this divergence of B. If B is known, in terms of x, y, z, or in terms of spherical polar coordinates r, theta, phi, or cylindrical coordinates s, phi, z, these are space points to tell the which point in space. You can tell what is x, y, z if you are using Cartesian coordinates, or r, theta, phi if you are using spherical coordinates, or s, phi, z if you are using cylindrical coordinates. So, if you know this magnetic field in terms of the coordinates, you can write divergence of B without going through this operation, but this is the definition. Okay. From this definition we can write expressions which are easier to handle, not going into this much of geometry and algebra and limit and calculus. And what is that? What is that? That is given in the book that we are using, and this is an appendix. This is in appendix, yeah, appendix 1, 2, 3, 4, fourth appendix, right, divergence, gradient and curl. And here there are expressions. Let me write this expression, though I will not be using in this course for divergence for a very simple reason that I will be telling, but then let me just write the expression, and let me write it for the Cartesian coordinates only, or maybe cylindrical also. So, it says that divergence of any vector A, it is written in terms of A. Divergence of any vector A is delta Ax delta x plus delta Ay delta y plus del Az del z. So, what does it mean? It means that this vector A is known everywhere, therefore, you know it at x, y, z coordinates, and you take component along the x axis, that will be Ax, you take component along the y axis, that will be Ay, and then the z axis, that component is Az. But at different points of the space, all these components will have different values. and therefore this Ax is a function of, Ax depends on which space point you are talking. Ay is a function of which space point you are talking, and Az is a function of which space point you are talking. So Ax is a function of x, y and z. What you have to calculate is this function is to be differentiated. This function is to be differentiated with respect to x. Treat y and z as constant. That is this term. And this function is to be differentiated. This Ay is to be differentiated with respect to y, taking x and z constant during this differentiation, and Az is to be differentiated with respect to z, and then you get this. Add all these three and you get divergence of A. Yeah? It is a scalar quantity, no I cap, no j cap, no k cap. Here it is a dot product, scalar product, scalar quantity. So this thing is a scalar quantity. Then similarly you have expressions for spherical coordinates and cylindrical coordinates. For cylindrical coordinates, it is 1 by s, then del s of s into As, and plus 1 by s del phi of A phi, and plus del Az del z. So if this A vector is known as a function of s, phi and z, and the components will be in s direction, in phi direction and in z direction, these are the components, you will write A as s cap plus A phi cap plus Az z cap or k cap. So these As, A phi, Az, these are once again functions of Sy, s phi z. This is also function of s phi z. This is also function of s phi and z. So you construct this. Take this function, multiply by s. Now you have another function. Differentiate with respect to s, keeping phi and z as constant, and then multiply by 1 by s. Similarly do this, you will get divergence of A, the value of divergence of A. Remember, this is a scalar. So whether you use this, you finally get the same number. Now the most interesting thing is that if you use this expression, say this expression or corresponding expression which we wrote earlier, B is equal to mu naught over 4 pi, then j d tau, this is the most general kind of current element, cross r vector minus r prime vector, and then divided by r vector minus r prime vector mod cube. Okay, and vary this r, not this r prime. So this is our integration of this, of course, integration of this with the entire current distribution. That is the magnetic field. Now it is integration over r prime. Okay, remember this integration is over r prime. This integration, what I am doing, this is the current distribution. I take a small part, this is d tau prime, and I see what is the current here. So current density is j d tau, and then the field point is here. The field point is here. This is r vector, and this is r prime vector, right? So with r vector and r prime vector, we do all this analysis, and get the magnetic field here. But now I want to know divergence of B. I want to know divergence of B. For that I have to differentiate with respect to x, y, z or s, phi, z, etc. Now this differentiation is what is the field here and what is the field here. This is that dx, dy, dz. Okay, if I am going from here to here, how much is x changed, how much is y changed, how much is z changed. So that x, y, z as a function of x, y, z, I am writing this B and then I am differentiating to get this divergence of B. So remember this minute statement that integration, when I am doing integration, this integration is on primed quantity. That means this d tau prime, this r prime, that we have to change and do the whole integration on this current distribution. But when I am talking of divergence of B, so that will be let me write once again that expression. It is divergence of what? B. What is B? B is mu naught over 4 pi and then integration and then j d tau prime and cross r minus r prime divided by mod r minus r prime cube. So there is an integration involved and there is a differentiation involved. When you integrate with respect to primed quantities it is. But here when you are differentiating, then you are doing with unprimed quantity. X, y, z. Which x, y, z? Which x, y, z? This x, y, z. This x, y, z. This is x, y, z. With respect to this x, y, z, I am differentiating, and with respect to this x, y, z, x prime, y prime, z prime, I am integrating. So you have primed quantity, you have unprimed quantity, and since they are independent of each other, so ordering is not important. You integrate on r prime, get a function of r and then differentiate, or you first differentiate this with respect to this r quantity, unprimed quantity, and then after that differentiation then you integrate. That is also possible. That is also possible. Now the final statement of today's lecture: no matter what kind of current distribution you have, no matter what kind of current you have, it is a circular loop, it is a solenoid, it is a line, or it is some surface current. Surface can be of different nature, volume current, different kinds of volume distributions of current, whatever. You create magnetic field, you have a magnetic field in whatever way. Changing electric field also produces magnetic field without currents. Whatever way you have magnetic field, once you calculate divergence of B, that divergence of B is 0 always. One of the very fundamental laws of physics, one of the 4 Maxwell's equation for electromagnetic fields, divergence of B is always 0, no matter how you have produced that magnetic field, what kind of current distributions are involved, and so on and so forth. There is a big long calculations you will have to do to show that this is 0. To show that this is 0, there is a huge amount of algebra involved, but if you do that algebra, if you have patience to do that algebra, you will find that yes, starting from here the divergence finally turns out to be 0. Okay. So, in all cases, not only current distributions, as I told, even if it is the other way of creating magnetic field is your this changing electric field, there also the divergence B is 0. It is a universal law, divergence B is always 0. So, next time we will talk of another operation on vector field, and that is known as curl of the vector field.